Hello everyone, I am Rhea Grace B. Bernal, and for today's video, we're diving into an essential topic in the set theory, the verification of set laws, specifically the commutative, associative, and distributive laws. So you may be wondering, why do these laws matters? So these laws help us organize and analyze information correctly. So in real life, we use sets all the time, like finding how many students like math or science, or identifying who likes both. So without laws, it will be easy to double count or make mistakes. So in mathematics, these laws serves as consistent rules that guide us in simplifying expressions, predicting results, and solving problems logically. Think of them as the rule of the game for sets. When we follow them, we can always arrive at the correct answers. So today, we'll verify these laws using simple examples, Venn diagrams, and real-life situations to help you understand why they always work. So by the end of these seasons, you'll be able to confidently apply these laws to solve set problems with clarity and accuracy. So let's begin and discover how these set laws truly work.
So before we verify the laws, let's recall the two basic operation, union and intersection. So union written as a union B means combine everything in the set A and B. And an intersection written as A intersect B means take only what A and B have in common. So for example, set A is a set of 1, 2, and 3. And in the set B is a set of 3, 4, and 5. So in a union A, in union B, combine all the elements from both sets without repeating any items. When we combine them, the number 3 appears in both, but we write it only once. So A union B is equals to set 1, 2, 3, 4, and 5. And intersection A intersect B, meaning take only the elements that appears in both sets. So compare sets. A has 1, 2, and 3. B has the 3, 4, and 5. So the only number that appears in both A and B is 3. So A intersect B is equals to set 3. So next is the commutative law. Commutative law simple says the order does not matter. A rule that says changing the order of set does not change the result. Simple says that it's easy idea to understand the order does not matter. So whether we write A first or B first, the answer is the same. So for example, A union B is equals to B union A. So let's verify using this example. Set A is the set of 1, 2, and 3. And set B is the set of 3 and 4. So let's compute A union B. So combine all elements from A and B without repeating. So set 1, 2, 3, 4. And the result is in A union B is the set of 1, 2, 3, and 4. So compute the B union A. Combine all elements from B and A. So 3, 4, 1, and 2. So we remove duplicate. So it's equals to set 1, 2, 3, and 4. So the result of B union A is equals to 1, 2, 3, 4. B union A is the set of 1, 2, 3, 4. Same result, therefore the union operation is commutative. Now for the intersection, A intersect section B is the set of 3. And B intersection A is the set of 3. The only number that appears in both A and B is 3. Same in a B intersection A is 3. So same result again. So intersection is also commutative. So when we use Venn diagram, when we drew Venn diagram, no matter which set is placed on the left or right, the shaded region stays the same. This visually proves the commutative laws. So next is the associative laws. So associative laws tell us that grouping does not matter. It doesn't matter which sets you combine first, the result is the same. So in mathematical expression, the onion A and B, then the onion with C is equals the onion A, the onion of B, and C. So the intersection is A and B, then intersect with C equals A intersect the intersection of B and C. So for example, let P is equal to set 1, 2, 3, and set Q is equal to set 2 and 3, and for set R is a set of 3 and 4. So first expression, P union Q union R. So P union Q, combine P and Q without repeating, is equals to set 1, 2, and 3. Then 1, 2, and 3 union R combined with the R, so is equals to set of 1, 2, 3, and 4. So the result of P union Q union R is equals to 1, 2, 3, and 4. So the onion of P and Q, the onion with R, gives the set of 1, 2, 3, and 4. So the second expression is P union Q union R and Q. So Q union R combined to Q and R is equals to set of 2, 3, and 4. Then the PU is equals to 2, 3, and 4. So combine P 1, 2, 3, and 4. So the result is set 1, 2, 3, and 4. So the onion of Q and R gives the set of 1, 2, 3, 4. So in conclusion, both sides gives 1, 2, 3, 4. Therefore, the onion operation is associative. So both sides give set of 1, 2, 3, and 4. Both expression result is the same. Set onion operation is associative. So groupings doesn't matter. So in intersection, same happen with the intersection. So again, grouping does not matter. Intersection work the same way. The groupings of sets does not change the results. So for example, set P is a set of 1 and 2, and set Q is a set of 2 and 3, and set R is equals to set 2 and 4. So the first expression is P intersect Q and intersect R. So P intersect Q elements is both P and Q is 2, and intersect to R, the result is the set of 2. So the result of P union R union Q is equals to 2. So the second expression is P union Q union R. So Q union R is the elements of both Q and R is 2. So the elements of both P and, so the result is P in intersection Q intersect to R is equals to set of 2. So in conclusion, both expressions gives sets of 2. So the intersection is associative, meaning no matter we group the sets, the results stay the same. When we use Venn diagram, if we group A and B first or group B and C first, the final shaded region remain the same, no matter with the sets we combine. First, we shaded area representing the onion and intersection does not change, visually proving an associative laws. So next is the distributive law of set, means one operation can spread over another. So distributive law is a rule about how union and intersection interact, means tell us the idea one operation can spread over another. So we can apply one operation to each part of another operation and get the same results. So distributive law means one operation can spread over another. So there are two formulas. So the first one is the intersection of A with the union of B and C equals the union of A intersect B and A intersect C. And the second one is the union of A with the intersection of B and C equals the intersection of A union B and A union C. So now let's verify the first one with an example of A is equals the set of 2, 4, and 6. And is a set B is a set of 1, 2, and 3. And in the set C is a set of 2, 5, and 6. So now let's analyze the left side. So A intersection B union C. So in A union is 1, 2, 3, 5, and 6. In the left side, A intersection of B union C. So B union C combine B and C is a set of 1, 2, 3, 5, and 6. So in A intersection, elements is both A is 2 and 6. So in the left side is a set of 2 and 6. So the intersection of A with B union C gives the set of 2 and 6. So now in the right sides, A intersection B union A intersection C. So in A intersection B is equals to set of 2 and A intersection of B is equals to set of 2 and 6. So in union 2 and 6, in the right side, A union B is elements with both A and B is a set of 2. And the element both of A and C is the set of 2 and 6. So union set of 2, union set of 2 and 6. So the right side is the intersect B union A intersects to C gives the set of 2 and 6. So now in the conclusion, both sides match, therefore distributive law is verified. Since both sides gives the same set, the distributive law is correct. So now, let's apply set laws that something's real, student interest. So for example, the survey in math, 18 students, and in the science is 15 students, and in both is equals to 10 students. So using the union formula, M union S is equals to math plus science minus math intersect to science. So it's equals to 18 plus 15 minus 10. So the total of 23 students. So this correctly counts how many students like maths or science without double counting those who like both. So set laws help us clean data, avoid errors, and interpret information correctly. So for summary, commutative laws, order doesn't matter. So associative law grouping doesn't matter, and distributive law operation distributes. So we verify with examples, Venn diagram plus real world context. So understanding these laws helps you simplify expression, solve problems quickly, and analyze sets more confidence.
Thank you for listening. I hope these lessons helped you understand how set loss works and why they are important. If you have any questions, reactions, or want more examples, feel free to ask me. Have a great day and continue exploring mathematics.